So today I will continue studying teaching Newton's law of universal gravitation, which is the last title of section 3 chapter 1. Uh, According to early model of universe, Earth was the center of universe, and all other space objects, planets, stars, even the sun, all were revolving around the Earth. Center was the Earth, all other planets, all other stars, even the sun were revolving around the Earth. So for thousands of years, the scientists believed this way. But the first astronomer who proposed that, no, this is incorrect. The sun, Earth is not the center of the solar system. Sun is at the center of the solar system. This first scientist who was an astronomer is Johannes Kepler. So according to Kepler's model, all planets, including Earth, were following around the sun on elliptical paths. So planets move in nearly circular orbits. So nearly circular, it's called elliptical. So elliptical orbits around the sun. So elliptical orbits, ellipse, orbit shape of the orbit will be ellipse. Ellipse is not a circle, it's a bulged circle. So if this is a circle about this point, so ellipse is going to be a little bulged in the equator. So that's why ellipse will have two foci. One foci will be on one side of the ellipse, other foci will be on one focus will be on one side, other focus will be on the other side. And according to Kepler's model, the sun is located at one of these foci, in here or in there. So then all other planets, including the Earth, will follow this elliptical path around the sun. But Johannes Kepler has didn't have such big influence in the scientists in this era, in those years. Scientists continue to believe that still Earth was the center of the solar system until Sir Isaac Newton was able to derive an equation for elliptic path suggested by Kepler. So Kepler suggested this elliptic path, but the first mathematical equation is prepared or written by Sir Isaac Newton. Isaac Newton's influence was very strong in the Western world. That's why after Isaac Newton said that, yeah, this is correct, Kepler's proposals are correct, and after that he wrote equations about these paths, these elliptical paths. So then scientists started to think about and then talk about the sun-centered solar system. So what was the Isaac Newton's equations? That equation was about interaction between the space objects. According this interaction is known as Newton's law of universal gravitation. According to this law, every planets are following circular paths around the sun. Of course, we learned that if an object is moving a circular path or near a circular path, there must be a centripetal force keeping these planets around on this circular paths. So Newton defined that force. So according to Newton's explanation, the force that keeps these planets around the sun is gravitational force. This gravitational force was a field force that always exists between two masses. Remember, in the 11th grade, you classified force into two groups. One group was the contact forces, second group was the non-contact force. So this field gravitational force is non-contact force, which is a field force that always exists between two masses. And According to Newton's model, these objects are always attracted to one another. So gravitational force is a force which is only attractive, not repulsive. Remember, in the 11th grade you learned that there are also other forces like electrostatic force. Objects can repel each other like negative and positive, but gravitational force is only attractive force. Planets or the objects only attracts each other. So this field force always exists between two masses, between the large masses like the sun, earth, moon, and also exists between small objects like the desk in the classroom, or between two pens, or between two balls. So this force exists between subatomic world, between the electrons, between the protons. However, this force is very dominant in a micro world, outer space, but it is very less effective, not very effective in the subatomic world. So why is it like this? Why this force is very strong between the large masses, but not so strong between small masses? Because this gravitational force is directly proportional to product, yani multiplication of the object's masses. We are going to multiply mass 1 and mass 2. Not only depends on mass 1, not only depends on mass 2, depends on both masses m1 and m2. So consider two masses m1 and m2 at a distance of r. These two masses will attract with each other with a force Fg. And these two forces are equal in magnitude, opposite in directions, and acts on different objects. That's why these two forces, the force acting on the mass 1 and the force acting on mass 2, they are action-reaction pairs. Action-reaction pairs. Remember, action-reaction pairs have equal in magnitudes, opposite in direction, and acts on different objects. So the first force, one pair acts on mass 1, other pair acts on mass 2. So these two forces are, the force acting on these two objects, both of objects are directly proportional to product, yani multiplication of the object's masses m1 times m2. Right now here I am going to talk a bit about mathematics in here. What if one of these masses are doubled? If mass 1 is doubled, it becomes 2m1. If mass 2 is doubled, it becomes 2m2. So in this case, by what factor the force changes? Generally, Mr. Exam questions sometimes ask in this manner. So if both masses are doubled, so mass 1 becomes 2 mass 1, mass 2 becomes 2 mass 2, if both are doubled. So we are going to multiply these 2 and another 2. So 2 times 2 becomes 2 times 2 becomes 4. So 4 times mass 1, 1 times mass 2. As you see, the right side of this equation, this proportionality increased by a factor of 4. So left side also must increase by a factor of 4. So which means, so force must increase by a factor of 4 or must change by a factor of 4. What if more forces these masses are halved? So halved means changed by a factor of 2. So halved means changed by a factor of 2. So m1 is going to be m1 over 2, m2 is going to be m2 over 2. So both masses are halved. So in mathematics, we will multiply numerator and denominator. So result is going to be m1 times m2 divided by 2 times 2, it becomes 4. Which means if right side is divided by a factor of 4, so left side also must be divided by a factor of 4. That's why, so you will divide the force by 4. So it's going to be F over 4, which means F over 4 can be expressed by two ways. One of them, force decreases, because as you see, if you divide by a number by 4, a quantity by 4, it decreases. Force decreases by a factor of 4. We say it like this. However, there's one more expression. This F over 4 can be written 1 over 4 multiplied by F. So F over 4 and these are equal. So in mathematics, this is explained like this. Force changes. force changes by a factor of 1/4. This is also explained in this manner. Both are defining the same thing but in two different ways. One of them, because force is divided by 2, we say that force decreases by a factor of 4, and also it can be written as 1/4 times F, which means force changes by a factor of 1/4. And one quantity which affects the gravitational force was the mass, multiplication of the masses. Second one is the separation between the objects. So the gravitational force is inversely proportional to square of the separation between the bodies. Inversely proportional, 1/1 something, inversely proportional to what? Square of the separation. So that's why as the for separation increases, force decreases, or vice versa. As separation decreases, force increases, because they are inversely proportional. As separation increases, gravitational force decreases, or as separation decreases, gravitational force increases. So let's do some mathematics again in here. Say that separation doubles. You make this object increase the separation by 2. So if r becomes 2r, if separation is r, this separation is r. If it becomes 2r, if you make it twice as far, if objects are made twice as far, so you are going to write instead of r, of course, 2r. So in here you should get the square of 2 and the square of r, both must be squared. Square of 2 is 4, square of r is r squared. As you see, this term is divided by a number of 4. That's why force must decrease by a factor of 4. If right side is divided by 4, left side also must be divided by 4. So that's why force decreases by a factor of 4. This is explained like this: force decreases by a factor of, or force changes by a factor of 1/4. What if separation decreases, halved? Say that you initially there at the distance of r, later you make them closer to a distance of r/2 if separation is halved, changed by a factor of 2, which means r is going to be r/2. Let's insert instead of r/2. We should get square of r squared. Square of 2 is 4, so it becomes 1/r squared over 4. We are going to flip the number in the denominator, so it's going to be 4 multiplied by 1 divided by r squared, which becomes 4 divided by r squared. So as r decreases, of course, f must increase, but must increase by a factor of what? So 4, because we multiplied this by a number of 4. That's why force increases by a factor of 4, or changes by a factor of 4. This is sometimes some questions, ministry exam questions are given in this manner. That's why better to learn this. Now we will continue back to the equation. We have two parameters which affects the gravitational force. One of them is multiplication of both masses m1 times m2, and second one is the separation between the objects. So when we combine these two, but before that we should learn one more thing in here. The gravitational force is inversely proportional to square of the separation between the objects. Because the gravitational law changes with inverse square of the separation, this law in mathematics or in physics are known as the law of gravitational gravitation. Universal gravitation is an example of inverse square law, because the force changes by inverse square of separation between the bodies. So let's combine these two proportionality, which is F is proportional to force is proportional to m1 times m2 over r2. So this proportionality must be changed to an equality by inserting a constant. This constant is capital G, known as the Newton's universal gravitational constant, or universal constant of gravity, and this constant is 6.67 times 10 to the power of negative 11 Newton times meter square per kilogram squared. So let's solve a problem. Find the distance between 0.3 kilogram billiard ball and 0.4 kilogram billiard ball if the magnitude of the gravitational force is 8.92 times 10 to the power negative 11 Newton. So masses are given. There are two billiard balls, one in here, the other one is in there. So mass 1 and mass 2. And force is given. Both are attracting each other with the same force Fg, which is equal to 8.92 times 10 to the power negative 11 Newton. And questions calculate the separation between these two forces. So M1 is 0.3 kilogram, M2 is 0.4 kilogram, and if these billiard balls attract one another with a force of 8.922 times 10 to the power negative 11 Newton, find the separation between these two balls. So equation is Fg capital G mass 1 mass 2 divided by r squared. This calculates Fg, but we should calculate r. That's why we should cross product first. Fg and r must be multiplied. Fg times r is equal to, so G times m1 times m2. R squared times Fg is equal to G times m1 times m2. So we are going to calculate r. That's why we have to divide both sides of the equation by Fg. So Fg will simplify. We will get the equation for r squared, which is G m1 m2 divided by Fg. After that, get the square root of equation, which is going to be G m1 m2 divided by Fg. Root of G m1 m2 divided by Fg. After that, insert the given in the equation. So G is 6.67 times 10 to the power negative 11. M1 is 0.3 kilograms. M2 is 0.4 kilograms. And Fg is 8.92 times 10 to the power negative 11. In here, don't forget two brackets. One bracket is common for the expression inside the root. Second one is for the denominator, because there's a multiplication. If there's a multiplication, denominator always use a bracket. So result is going to be 0.3 meters if you do this calculation. And this is how we calculate the gravitational force between any two objects, and these objects will attract each other with the same force of magnitude but opposite in directions, action-reaction pairs. And by the help of this law, we are able to derive an equation about calculating the free fall acceleration of the Earth or any other planet. Remember, free fall acceleration of the Earth is ag, or sometimes it's only g, is equal to 9.81 meters per second square. This number can change at different parts of the Earth because Earth is not a perfect sphere. It's a little bulge. Sometimes it's called bulge. It's not perfect, something like this. That's why it's possible different part of the Earth can have a slightly different free fall acceleration, but on average it's 9.81 meters per second square. So now we are going to show derive an equation for calculating free fall acceleration on the surface of the Earth. So because Earth is a very huge body, we are going to, and it's almost a perfect sphere. Not perfect, but almost perfect. So we can assume that the whole mass of the Earth is concentrated at the center of the sphere in here. So mass of the Earth is concentrated in here. And a man I located on the surface of the Earth, and the mass of this man is small m. And I want to calculate what is the free fall acceleration at the location of this man. So to get this, I'm going to use two definitions of gravitational force. One definition we already learned according to Newton's law of universal gravitation. I can write this force Fg acting on the man's body. Second one is by using Newton's second law of motion, which is known as weight. We can also write this gravitational force. One of them we already learned. Gravitation, universal law of gravity, capital G, mass of the first object, which is the Earth, mass of Earth. Second object is man, small m, and separation between them is from center of the Earth to the man is the radius of the Earth, re squared. Second equation is I'm going to write according to Newton's second law. Remember, F is equal to mass times acceleration, but in here acceleration is free fall acceleration. That's why I'm going to write this equation by Fg, mass times g, which is the weight of man. These two equations are defining the same thing. That's why we can use, we can make them equal. So m times g, which is the Newton gravitational force according to Newton's second law, is equal to capital G, mass of Earth, multiplied by mass of man divided by radius of Earth squared. As you see, mass, because mass is on both sides of the equation, so they will simplify and you will get the equation for calculating free fall acceleration on the surface of the Earth. So this equation can be used not only for the Earth. You can calculate free fall acceleration of any planet, provided that the mass of that planet and radius of the planet are given or is known. So now we are going to comment on this equation. This equation tells you that free fall acceleration of Earth or another planet depends on two things. One of them is G is directly proportional to mass of the planet. As mass of the planet increases, so the free fall acceleration increases. Second one is inversely proportional to square of the distance between from the center of the planet. So when you go up away from the center, so because R increases, free fall acceleration decreases. So that's why when you go up to the sky, the free fall acceleration becomes less than the surface of the Earth, or at free fall acceleration at the top of a mountain is greater than the free fall acceleration on the surface or at the sea level. Here is a question, chapter question about this. Question saying that comment on statement there is no gravity in outer space. So in fact it's explaining that as you go to space from the center of the Earth, if you go away and away, what is increasing? R is increasing. As R increases, according to this equation, free fall acceleration decreases. If you go so far from Earth into the outer space, in this case, R is going to be so big. That's why gravitational field strength will be so small. Almost it's going to be equal to zero. There is no gravity in outer space is normally explaining this fact.